Please, the floor is yours.
Okay, thank you. So my name is Cunha. This is based on joint work with Kasper and Larsen, which is here today, and Martin Ritzert. So I normally start with an introduction to classification, but I think we saw many times today, so I'll still do it, but more quickly. So I have a domain of inputs X and a data distribution over it, the classical example being a domain of pictures of cats and dogs. And we have a label space that we'll assume to be binary here for simplicity. The usual one is cat and dog. And we have a target concept that we're trying to learn that is mapping the pictures to the right label. More abstractly, we'll consider inputs, generic inputs X index I and labels plus and minus 1. And in the drawings that we'll have, we represent this like you can see where this notations means that the hypothesis C associates the label plus 1 to the first input. So the difficulty in this setting is that the C can have a very large domain, even infinite, and we don't see it directly. We only see some samples, IID samples from the distribution, which will consist, which will be our training data. And this notation here, sometimes people are not that used to it. It's like the restriction of a function to the given set. So given this training data, we want to a learning algorithm that produces a hypothesis that approximates C not only on the training data, but in the entire domain with high probability. More formally, a strong learner is what we've seen a few times today. We have given accuracy and confidence parameters and given sufficiently many examples labeled by a target concept. We have that with high probability the produced classifier approximates C on the entire domain. Or more formally, we have that with probability at least 1 minus delta, the probability of the classifier making a mistake on a new sample from the data distribution is at most epsilon. So we will try to build this in this talk. We will try to build this learner with using sample compression, which we also got a talk today. And the example that I have is exactly the same one that he gave at his talk. So SVM for the win. So we started with some points sampled from the distribution, and we see the labels according to the target concept. And then we produce a hypothesis that is consistent with the training data. It classifies the same way that the target would. And we are interested in the setting where with this hypothesis can be obtained from just a few samples that I have highlighted, with the extra property that if you discard that you also mentioned that if you discard some of the points that are not in this compression sample, in those special points, then the hypothesis obtained remains unchanged. This notion has been formalized before by previous works in the following definition of a stable sample compression scheme, where I have a pair of functions, one for the compression, that taken the sample reduces it to a subsample, to a compression set of size at most L, and the reconstruction function rho that given the compression of a sample labeled according to a target function, produces a hypothesis that within the sample is indistinguishable from the target function. So in particular, it means that it's correct in all the points of the sample. It doesn't really need to be the same, but it needs to be consistent. And we have this extra property that it's stable, meaning that if you compress any subset of the given sample, where the subset maintains all the points that were in the compression set, the compression just doesn't change. So with this definition, previous work by Busquet, Haneke, Moran, and Zivotowski, they show that the reconstruction function has this error bound with a probability at least 1 minus epsilon, where the stability property that I highlighted there, it removes the log m bounded from from previous work by Littlestone and Wormuth. So yeah, but with this stability, you get rid of this log m. So our contribution is to propose a randomized version of this sample compression scheme, where the definition of a stable randomized sample compression scheme of size L with failure probability delta is getting quite big. You have a pair, and instead of a compression map, you have a distribution of maps for encoding. And the reconstruction is not random, it's like before, except that it doesn't need to reconstruct perfectly all possible maps. It can fail with probability delta. And the notion of stability here is trying to capture the same, right? Removing points that are not in the compression set maintains things as before, which in this settings means that the probability distribution doesn't change, or more formally, if you remove points from a sample Z to obtain Z prime, compressing Z prime behaves, has the same distribution as compressing the whole Z if you know that the points in the compression of Z are still in Z prime. So with this distribution, we proved the result that's very close to as the analogous and with the same error bounds that you had in Busquets. The proof sketch, one of the good things is that this is quite smooth. How am I doing time?
You're doing well.
Good. So the proof sketch, one of the cool things of compression is that I think it gives a very nice proof. So, and this one is particularly clean, like the previous work. Where you just take the points sampled from the data and consider the labeling and separate those into, you just partition in 2L rows or parts. And when you consider the points in the compression set that I highlighted in a very dark shade of blue, we know that at most L of those rows will contain all of the points, right? So by the stability property, the distribution that we obtain when compressing just the union of those rows will be the same as the distribution we would have by compressing them all, distribution of the compression maps. And by the definition of the portion about the stability of the reconstruction, we know that the sample is correct on the entire thing, even though we could consider a compression just as a function of those highlighted lines containing the compression points. So the idea from there is just to bound the probability that the obtained hypothesis has a high error rate, but still performs well in this validation set, in those points, in those untouched rows. So yeah, the idea is to bound that. It would be unlikely, right, that this happens, and then you can just union bound by on the choice of the possible choices of I, and you pretty much get the result. So we did this work when we started it, we had an application to boosting in mind. So I'll go for a quick review of boosting. So we had the definition that we had before, and also in the other talks of the strong learner that can get arbitrarily small error with arbitrarily large probability. And this is quite a strong definition because this is true error, right? So it would be natural to consider if we can obtain good performance starting from a weaker notion of learning, which is the notion of weak learner. Where I get the training data and produce the weak learner takes the training data to produce a hypothesis that is just gamma better than random guessing, which is not that much, right? It's much softer. But with the advantage that we have, we can choose how to weight this training data. It doesn't need to be the uniform distribution. You can get a very different probability distribution of the training data, and it will still return a hypothesis whose mass of correctness is at least 50% of the total, 50% plus the advantage gamma. So the standard way to, I have a more formal definition here, which is an algorithm that we represent just by W that gets a sample labeled according to a target concept. And for any distribution over the sample, it returns a classifier that approximates the target concept a bit better than random chance. And this is the formal definition. The probability of making a mistake given the distribution is at most half minus gamma. So the usual way to turn those weak learners into strong learners is the iconic ADA boost, where you just start with the uniform distribution over the training data and feed it to the weak learner to obtain a hypothesis that's slightly better than random. But then you use this, you change the distribution to focus on the examples that were answered wrong and reduce the weight of the examples that were answered correctly, and feed the new distribution to the weak learner to obtain a new hypothesis, and that goes on where you are focusing on the hard examples, right? By the end, you will obtain, you just take all the hypotheses obtained and aggregate them by majority voting. And we know that this gives, if you do that not for 3, but for a sufficient amount of rounds, then you obtain this error bound. So there is a lower bound showing that you cannot do much better than this for voting classifiers if you query the weak learner with a distribution over the full sample. So, and there are also some results that give a better error bounds, but not using voting classifiers. So what we ask, the question we're trying to answer is whether you can do better than this using just voting classifiers, right? And since there is already a hint, right, that the trick has to be in not using distributions over the entire sample. So what we do is to boost by subsampling. So instead of feeding the distribution directly to the weak learner, we obtain first a subsample and give this to the weak learner just with the uniform distribution over it, which is just getting 50% plus gamma correct. And then by classical learning theory results, you can see that if this subsample is large enough, then the performance on the subsample is going to be close to the performance on the entire sample. And we just pass by the algorithm here. It's not that different from other boosts, except that we have a fixed learning rate, and also we get a fixed subsample size and a fixed amount of rounds to run for. But we also start with the uniform distribution and then do what we just discussed. We do the sampling and obtain the hypothesis by calling the weak learner on the subsample. Then we do a normal ADA boost update. The natural compression, random compression that we're obtaining here is just the sequence of those subsamples. And to reconstruct it, we just call the weak learner on each subsample. And since the associated randomized compression scheme is stable, we can show that. And then using the theorem that we just saw, we can remove a log factor from the previous bound. So this is the error that we get at the end, but on the right you have like the normal error. This comes because our proof also uses like large margins, which is the standard argument for proving results on boosting. And then we get this new one where you can see that this log factor died, but yeah, there is some trade-off. You gain some stronger dependency on gamma. Yep, that's it.
If I'm not incorrect, randomized scoring scheme implies deterministic stable complexity.
Yeah.
So can you just do the same analysis with the stable? Like, do you have to use the randomized complexity?
Yeah, we thought a bit about that. It seems to be the case, like because like we started the presentation a bit perhaps backwards from what happened. We're thinking about boosting, and it's hard to think of. Because boosting, then you have those dependencies, like we needed to know what came from the previous step to decide what we went on to, what goes into the next. So we weren't able to untangle those things in the analysis. So it might, yep.
So is there any chance to remove this gamma to the power of 4 from the denominator, or is it just?
Yes, well, kind of. When we started, we thought, perhaps. No, but
so it's a limitation of 3 for the voting, or?
It's not. I'm not entirely sure, but yeah, I just don't see a way we could do that. We thought a bit about it.